B7, the binomial expansion. We take the binomial a plus b and raise it to a power. Power n, where n is equal to 0, 1, 2, 3, and so on. Now, if n is equal to 0, then anything here to the 0th power is going to be 1. So a plus b, that quantity to the 0th power, is equal to 1. If n is equal to 1, then a plus b to the first power would simply be a plus b. For n equal 2, we would have a plus b, that quantity squared, and that would be a squared plus 2ab plus b squared. Now, if we want it cubed, n is 3, a plus b cubed would be, we would take the one we just calculated, a squared plus 2ab plus b squared, and multiply that by a plus b. Now, if I do that, I would get, coming in here with the a first, use the distributive axiom. So this is a cubed plus 2a squared b plus a b squared. Now, coming in with the b, we'd have a squared b, so that's another one of these. And then we would have here 2ab squared, so that's another one of these, well, two of them. And then we would have b cubed. So then we would add these up, and we would get a cubed plus 3 a squared b plus 3 ab squared plus b cubed. Now I'd like to do one more. Let's take the case n equal to 4. So we would multiply this one here by a plus b again. So if we do that, we would have a to the 4th power plus a cubed with the 3b in there, so that's 3 a cubed b. Then when the a hits this one, we would have another 3. We have another 3, and that would be an a squared, and then b squared hangs around. And then when a hits the last one, we would have an a b cubed. Now notice that the sum of the powers always equals 4. You can think here the b is to the 0th power. Here b is to the 1st power. So that's kind of neat to notice that. And then if we multiply with the b, we would get ba cubed. So that's another one of these, ba cubed. Then we'd have 3a squared b squared. That's another one of these. Then we'd have 3ab cubed. That's another one of these. And then we would have a b to the 4th power. And then we would want to add all those up to get our a plus b to the 4th power. So that would be a to the 4th plus 4 a cubed b plus 6 a squared b squared plus 4 a b cubed plus b to the fourth. Now, Pascal discovered an interesting result here. If you make a triangle with one along each of the sides sloping down like this, like a tree, then you come in here, and between these two you put a 2, you add those, then you add 1 and 2 to get a 3, 2 and 1 to get a 3, then 1 and 3 to get a 4, 3 and 3 to get a 6, 3 and 1 to get a 4, 1 plus 4 is 5, and this would be 10, this would be 10, this would be 5, and that would be 1. These are the coefficients that we have found. For example, in this first case, if you have a plus b to the 0th power, you just get a 1. In the second case, you have a plus b to the 1st power, and you get a plus b. And you can think of this actually as a to the 0, b to the 0, and you can think of this as a to the 1, b to the 0, plus a to the 0, b to the 1. Then the next one, you would have, this is a plus b squared, and you would have here a squared b to the 0th plus 2 a to the 1, b to the 1 plus a to the 0th b squared. So it's kind of interesting how the powers, the exponents, here add up to 0. 0 plus 0 is 0. 1 plus 0 is 1. And then 2 plus 0, or 1 plus 1, that's 2. And this one here is the one we found up there. Say 1, 3, 3, 1. And this one here, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Now we would like to have a way to figure these out quicker rather than have to multiply all that stuff out and take that much time. So what we're going to do is consider little baskets here where each one has an apple and a banana. Apple and a banana. So actually this one here, this is the 0th case, 1, 2. This is the 3rd case, so you'd have 3 baskets. So the question is, how many ways can I pick all apples? See, if I pick all apples, that's going to be the a cubed one, and no bananas. So I could emphasize that by putting, B0. Well, there's only one way to do that. You have to pick one from each basket. So there's one way. So the coefficient in front is 1. That's this one here. Now, how many ways can I pick 2 apples and 1 banana? Well, I can think the banana first. How many ways can I pick a banana? Well, there's 3 ways. 1, 2, 3. Pick it from each one. So therefore, that's going to get me 3, whereas 2 apples and 1 banana. And due to the symmetry, if I were to pick the apple, there'd be 3 ways to pick the apple, a single apple, and I'd have then 2 bananas. And by symmetry, the last one here is going to be a coefficient of 1. It's going to be no apple and 3 bananas. But I would like to analyze this one here by picking the apples first. This is the key to understanding this whole scheme. If I pick the banana, it's straightforward. There's only 3 ways. We're finished. But if we pick the apple, if I pick the apple first, for this one, there's 3 ways to pick the first apple, but then there's 2 ways to pick the second one. But I know the answer is not 6. The answer has to be 3. Because doing it the easy way, picking the banana, there's only 3 ways. So what happened here is that the order doesn't matter. Yes, there's 6 ways, but it doesn't matter which apple is first. The apples are not labeled, they're not named. So therefore I have to divide this by 2. And then I wind up getting 3. But now an interesting thing starts to happen. I can think 3 times 2 times 1 refers to picking fruit. How many ways can I pick the first fruit? 3 ways. Second fruit, 2. And the last fruit, well, I'm stuck with the last basket, 1. But what did I pick? I picked here 2 apples. So I had to divide by 2. I'm going to make that 2 factorial. And then I divide by 1 factorial. And this is nothing more than 3 factorial. So this is a key to understanding this whole mystery here. 3 pieces of fruit, 3 factorial, and then if there's 2 apples, it doesn't matter the order, so I can swap them either way, so I have to divide by 2 so I don't overcount. And then since I have 1 banana, that's not a problem, it's just 1 factorial. Could this be the general formula? Could it be this simple? Could it be, let's check with this case here. Here I have 4 baskets. A, B, apple, banana, and apple, banana. How many ways can I pick? This first one, remember, is going to be your apple, or your A to the 4th power. How many ways can I pick all apples? Then this is going to be 1 less apple, 3 apples, 2 apples, 1 apple, and 0 apples. Well, to pick 4 apples, there's only 1 way. You got to pick 1 for each one. See? What about picking 1 banana, which would be the next case? This next case here is 3 apples and 1 banana. Well, there's only 4 ways. I picked the 4 ways, so the answer is 4. But now I want to do this one, forcing myself to pick the apple first, because I know the answer is 4. Because if I think bananas, 1, 2, there's 4 ways. 1, 2, 3, 4. The answer is 4, and that's what that is right in here. But now if I pick the apple first, there's 4 ways to pick the apple. And I'm going for 3 apples. So it's 4 ways to pick the first one, 3 ways to pick the second one, and 2 ways to pick the last one. So let's focus on the 3 apples. Suppose the apples were numbered. Suppose we had 1, 2, 3. We had numbers painted on the apples. Well, how many ways can we arrange them? Well, we could have them set up like this, or swap these 2. We could swap the first 2, 2, 1, 3, and then I could have here 2, 3, 1, and I could have 3, 1, 2, and 3, 2, 1. So there are 6 ways I could arrange the 3 apples. So if the order doesn't matter, I got to divide by the 6. I mean, there's 1, 2, 3. The numbers have to be different. They're labeled. I have 1, 2, 3. I swapped here the last 2, 1, 3, 2. And see, there's a pair of each one with the 1s first, the 2s first, and the 3s first. That takes care of all 6 cases. So I know I need to divide this by 3 times 2. But I put a 1 here and a 1 there. And since I have 1 banana, I could have a 1 there. So in other words, this is fulfilling the formula that we had earlier, where we took the number of fruit, 4 factorial, and then we had 3 apples and 1 banana. So could it be that the general formula is n for the number of fruit, n factorial, and then say we pick k apples, we would have then k factorial, and then this is for bananas, you would have n minus k. I mean, could that be it? All right. Well, let's check this one in here, this 6th one. All right, so we come down here. So this would be here picking, let's see, it's 4 apples, 3 apples, 2 apples. So it's 2 each, 2 apples and two bananas. So that would be, I'm picking 4 pieces of fruit. So I would put the 4 factorial. And then I'm picking 2 apples and 2 bananas. See, it doesn't matter the order. It says I'm picking 2 of each. I divide by 2 twice. But using our formula, that's what we would do. And that's equal to here, 24. This is equal to 24, because 4 times 3, well, let's just work it out. 4 times 3 times 2 times 1. That's going to be 12 times 2, 24. And then we're going to divide by 2 twice. Well, if you divide by 2 twice, this 2 times 2 will cancel that 4. You get 6. Well, that's what it is. It's 6. It checks out. And because of the symmetry, these are going to work the same way. If you have, say, 3 apples and 1 banana, 3 bananas and 1 apple are going to work the same way. Well, let's check out one from the 5. So here's 5 apples, 4 apples, 3 apples. All right, 3 apples, 2 bananas. So let's check this out. We have 5 pieces of fruit, and we have 5, 4, 3 apples. And since we have 5 pieces of fruit, that's 2 for the bananas. Notice that this is 5 times 4 times 3 times 2 times 1. And we're going to go 3 times 2 times 1, and then 2 times 1. So these go, and then 2 goes into 4 2 times, and then 2 times 5 is 10. It checks out. So this is the general formula right here. So when we want to add them all up, we're going to add up the cases. Let's look at, say here, we're going to go from k is equal to 0 up into 2n. So you can think of this, apples or bananas, it doesn't matter because it's symmetric. So we can think of this as 0 apples, and then there's a 1 apple term, there's a 2 apple term, there's a 3 apple term, until you get to n apples. So this would be then here, we would have n factorial, and then we would divide by k factorial, the number of apples or bananas because of the symmetry, but we'll say apples. And then here, n minus k, the number of bananas. So therefore, apples go with k, and bananas go with n minus k. And because of the symmetry, you get the same result if you have a and b interchanged. So this would be equal to a plus b to the nth power. Now don't let this little summation sign scare you. That means let k equal 0, and then let k equal 1 and k equal 2, and then you'll get all the terms. Notice that when k is 0, 0 factorial, we want it to be 1 for it to work. Now we can test this with the case n is equal to 4, which we worked out in detail. So the first term would be k is equal to 0. So we have 4 factorial for all these. So 4 factorial, but then you would have 0 factorial. And you would have here 4 minus 0 is 4 factorial. So this is going to be 1, and that's going to have here no apples. And this would be 4 bananas. Okay, like that. Or vice versa, either order, doesn't really matter. And then the next term would be 4 factorial over 1 apple and 3 bananas. 1 apple and 3 bananas. And you could see that you're going to get 4, because the 3 factorial, well, just 4 times 3 factorial, you just get the 4. And then if you have 4 factorial with, say, you keep increasing the apples and decreasing the bananas, like this, that would be 2 of each. We already worked this out. This is what we got earlier when we looked at the 2, 2, right here. You already did this. And that gave us 6. So this checks out very nicely. And just to emphasize, you could go from 0 to n, n factorial over k factorial, n minus k factorial, and you could put a, n minus k, and bk. You can switch the apples and bananas because there's symmetry here. There's a symmetry that is very, very beautiful to see. So in this case, you start off with, say, all of them being apples, kind of like we were working out these formulas here. So you could pick any way to remember that formula. So the formulas are equivalent. I think probably you'd find this one because you write a first. AK looks simpler, a to the k power. You probably would write it like this. All right, that's the binomial expansion. And I remember when I was an undergraduate, I asked the calculus teacher, would it still work if n is like a half? And he looked at me and said, yes. Now, we're not going to get into that, and that can get quite complicated, but this is a very powerful formula, the binomial expansion. So that summation symbol that you see there at the start, where it has k equals 0 to 4, that means you let k equal the various values and put a plus sign in between the terms. So we have 5 terms written out using the formula. Then we can simplify a little bit here by working out what the terms are. And this is a summary of what we have done already. And then we can simplify further and let a to the 0th power be 1. And a to the first power, just write down a. And then finally, because of the symmetry in a and b, we can have a fourth first rather than b fourth first. So I have the formula written in both ways, and maybe some days I like to have that a fourth first, since I think about that when I do the binomials. Maybe other days I might not prefer that. So it's subjective. Either way works fine.